In this warm-up, I'm introducing the two special cases of no solution and infinitely many solutions with a system solving a system of equations using the elimination or linear combination. I've already introduced the special cases with substitution, and now we talk about the steps that you need to make sure they're in standard form. The first set of problems, the first two equations, is in standard form. So then I have to create opposites. I created them in the x column by multiplying a -2 through the second equation, -2x plus 4y equals -8. And then we added the two equations together, and we ended up with the variables eliminating in both columns, and so 0 equals 0, which is always true. So that means that they're the same line on the graph, so we talk about what that means graphically. And so graphically it means that you're only going to have one line on the graph, because they're the exact same line, and therefore they share all the points in infinitely many solutions. Algebraically, we talk about if the variables eliminate, you end up with 0 equals 0, 3 equals 3, -2 equals -2, and it's always true, or we can test it by plugging in any real number, and it'll make both equations true for any real number. And we talk about what else can you tell about the pattern of these two equations? Well, also the top equation is a multiple of the bottom equations. So if you multiply the 2 through the equation, they're the exact same equation, and therefore they represent the same line on the graph, and we've talked about that before. And then we talk about, well, what do you have to state? You can't just leave it algebraically as 0 equals 0, or 3 equals 3, or -2 equals -2. You actually have to state one of the three solutions, which is infinitely many solutions. And then we talked about the second problem is that both variables eliminate also when you create opposites. On this one I had to put the second equation in standard form. That's the first step to make sure they're lined up, the x column, the y column, the equal sign, and the constants. And then I created opposites. I didn't have to create opposites, so I skipped step 2. They already had opposites in the x and the y column, so they eliminated, and I ended up with 0 was not equal to 7. Therefore that's never going to be true. 0 will never be equal to 7, so no solution. And so graphically, what does that mean when there's no solution? That means that these two lines are parallel. In fact, if you put both of them in slope-intercept form, you'll see that they have the same slope, and therefore they share no common points, and so no solution in common. And so you're going to have, algebraically, it's going to look like if you eliminate both variables, 0 equals 7, 2 equals 1, -1 equals +1. They're never going to be true. And then you actually have to state no solution. And if you're going to put the reason, you would put because they're parallel lines and they share no points. And then the last type that we needed to review was intersecting lines that I didn't show in the warm-up that we've done a lot with, which means they share only one common point. Algebraically, you'll actually get a value for x and a value for y. So if you ever get a value for x or y, you'll get a value for the other one, because it means that the two lines are intersecting, and therefore you just state the solution of whatever point that they intersected at.